All right, so we talked about bond lengths, now bond energies. 151 kilojoules per mole to break an iodine-iodine bond, which means visible light will break that easily. And so we got to protect iodine from light. Some other especially weak bonds, or take a look at the oxygen-oxygen bond. The oxygen-oxygen bond is called a peroxide link. The peroxide, look at that, 142. Is that the weakest bond here? The peroxide bond? It's the weakest bond here. It's even weaker than iodine, and iodine's got a weak bond. So that's saying something. So some of the stronger bonds. Here, what's the strongest bond you see? Is that it? Yes, this is. Nitrogen-nitrogen triple bond. Nitrogen is called a pseudo-inert gas. The reason it's called a pseudo-inert gas is because it's so unreactive. And one of the reasons it's so unreactive is look at that bond energy. The triple bond's especially strong. That's a huge bond energy, 1,000 kilojoules per mole. It's hard to break. And so that means the nitrogen in this room is pretty unreactive. I guess you could call it non-toxic, but it's nitrogen is very toxic. People who work with liquid nitrogen, I guess in Las Vegas somebody froze from liquid nitrogen, so there it was quite toxic, and other people have asphyxiated themselves from nitrogen. And so that's that. All right, so those are some bond energies. In other words, what's the trend? So when you look at charts like this, you try to get a trend. And the trend is that the longer the bond, the weaker it is, right? And the shorter bond, the stronger it is. And as the bond order increases, bond order will be single, double, triple, 1, 2, 3. The bond strength increases. All right, now I just need to say something about some more complicated Lewis structures. So let's talk about more advanced topics in Lewis structures. So these are the basics. The advanced comes in, and comes when we have a scenario like this. Expanded octets versus formal charge. And so if we look at a structure, let's come up with a structure like this. This is going to be OPCl3. This is a neutral molecule. It's going to have a, what's the geometry of this? What do you think the geometry of this is? We got 4 single bonds. Tetrahedral. How about the OPCl angle? What's the OPCl angle? 109. What's the CLP-Cl angle? 109. Do you expect much distortion? We don't expect much distortion because these are all single bonds. Although the atom sizes are different, chlorine's a lot bigger. And so there are going to be slight distortions, but not significant like we were talking about earlier. The distortions are going to be small here, and so we aren't even going to say it. We're just going to say the OPCl angle, 109, the CLP-Cl angle is 109. They're all single bonds. Now, when we look at the formal charges aren't looking so good. And so here, the formal charge on oxygen is minus, the formal charge on phosphorus is plus. And so one of the ways we can get rid of formal charges like this, when we got a minus and plus, is to create a multiple bond. Because what that's going to do is it's going to take some electron density off oxygen and give it to phosphorus here. And if we form a double bond here, like this, the formal charges go to 0. And so now all the formal charges are 0. And it looks good. And so what should we do? Should we expand the octet? Well, is phosphorus capable of expanding an octet? And so expanded octets this is the theory here. Expanded octets on phosphorus can happen because we're dealing with 3s, and we got the 3p's. This has a maximum capacity of 8 electrons. We bypass the 4s. We bypass the 4s because it's too far out, and then the 3d are closer. And so if we expand the octet, then we can throw some electrons in 3d and get more than 8 electrons. And so in this case, do we expand it? And so the structure you're going to see most is here, where the formal charges have been minimized, but we've expanded the octet in this case. All right, there is some argument for this. The argument for this is we don't expand the octet, and then what we have is we have a covalent bond here and an ionic bond. We have both bonds occurring. The covalent bond shown here, where there's some sharing of electrons. The ionic bonding is a separation of charge, and the opposite charges attract each other. And so there's an ionic component here. And so theory is there any d contribution? You know, are there electrons in d orbitals? To explain this, if there's no electron density, in d orbitals, then we're looking at something like this. So it is. But historically, it's been shown as this. Now, we're going to have other cases like that are going to be quite a bit more tricky. And so let's look at one particularly tricky one, perchlorate. Perchlorate, we do this here, and we get 4 oxygens. This structure seems pretty easy. Good. This would be the Lewis structure for perchlorate. Each oxygen has a negative formal charge, and this chlorine has a +3 formal charge. And so that when we add up all the formal charges, we'll get the net charge on the ion. The net charge on the ion is minus. It's -1 ion for chlorine. But one thing we have here is we have a very high formal charge, +3 on the chlorine. And so in this structure, you know, all those electrons went to oxygen. You know, the formal charge is quite a bit different than oxidation state. You know, in the oxidation state, you're just imagining the bonds being totally ionic and then figuring out what its apparent charge is. But formal charge is real. This is real because we put all the electrons in the oxygen, leaving chlorine with a deficit of electrons here. What's the shape of this? This is tetrahedral. The same thing, what's the shape of this? This is tetrahedral, but now the bonds are going to be distorted. The OP-Cl bond is going to be greater than 109. The ClP-Cl bond is going to be less than 109. So this will be about 111. This will be about 107 because of the double bond here. That's another way we could see. Well, this will be tetrahedral. But, you know, this +3 makes me uncomfortable. And so this is what we'll call structure 1. And then we're going to have structure 2. Structure 2, well, this is having an octet, and the bonding is going to be quite ionic because there should be a very large contribution from ionic bonding because +3 and -1 is going to form a strong ionic bond, pulling them together. Okay, but we'll say, that +2 +3 is bothering me, so let's at least form 1 double bond. If we form 1 double bond here, then it's going to look like this. You know, double bonds are shorter. And so forming 1 double bond there is going to drop this formal charge to 0, but we'll still have minus, minus, minus here, and now it's dropped to +2 versus +3. And so +2 should be, that should be better because we're only losing 2 electrons. I mean, chlorine's pretty electronegative, isn't it? And so you'd expect that. With a structure like this, how many resonance forms can we draw out? Well, the number of resonance forms we can draw out is we could have picked this oxygen, which we did, or we could have picked this oxygen, or this oxygen, or this oxygen. Actually, all 4 oxygens are possible. And so what we'll do is we'll just move the double bond. We can move the double bond here. And so we'll generate this resonance form. It's minus. Actually, then we could move, we don't move the atoms. So we move the double bond here, we can move the double bond here. Like this. That's 3 resonance forms. And then finally, we can move the double bond on the bottom. Like this. And the formal charge is all there. You know, the 0 went here. This is negative, 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 plus 2. 0 goes over here now. This is negative, 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 plus 2. The plus 2 stays on chlorine. This is plus 2 here, negative, negative, and negative. And this is 0 here. And so what is the, we got 4 resonance forms. And so the hybrid is going to look like what? The hybrid is going to look like this, where there's 4 single bonds attached to each oxygen. And then that double bond is what we call delocalized. Delocalized means it's spread out over the 4 bonds here. And so that means, well, if we have one double that's spread out over 4, then each of these bonds is what we call a 1 1/4 bond, or a 1.25 bond order. This is a 1.25 bond. They're all the same. And then the charge, well, we have -3 spread out over 4. So -3 spread out over 4 gives me a -3/4 charge on each. Because -3/4 times 4 oxygens will give us a net charge of -3. And so each one is -3/4. And this would be tetrahedral. All the bonds are the same. What's the OCLO angle? 109. It should be perfect because all the bonds are the same. They're going to have the same distortion. Which is, okay. And so this is the hybrid structure. Right? For this. Series 2, we call it. But you know what? I'm still, because earlier I talked about having the +2 formal charge. +2 formal, that's like I1, I2, you know? Second ionization energy is like double the first ionization energy. And so, well, that's if it's valence, and this would be valence. So I'm still, I still don't like that formal charge, but you know what? I can get rid of that formal charge a little bit more. How can I get rid of that formal charge a little more? Well, to decrease that formal charge further, I can do this. I can form 2 double bonds. If I form 2 double bonds like this, then what happens to the formal charge? Well, this one's negative, these are 0, and this goes to plus. So the formal charge dropped down to plus. How many resonance forms can I draw for this? You know, I'm not going to draw them all out completely. I have, okay, the thing is, I leave one double bond in place and then see all the other possibilities. Well, one possibility was down, the other possibility is left. So we have the left, and then leave the top one in place, and then what are the other possibilities? The other possibility is right. And then I'll move it down, so I'll make a single bond on the top. I'll make a single bond on the top, then what are my other possibilities? Well, I have double bond here, like this. But, hey, wait a minute, isn't that the same as this? Are these two structures the same? Yeah, they look the same, but they're actually different, because the way you can tell that they're different is you pin the atoms on the page. And when we're looking at resonance, we're just looking at if the atoms are fixed on the page, is there another way to distribute the electron density? And so the answer is yes. So this is actually a unique structure here because I never move the atoms. The only way to make these two equal is if I take the atoms and rotate it. But you can't rotate the atoms. The atoms must stay fixed. And so we have this one where we got that. And are there any other possibilities? Yeah, okay, we'll leave it on the left now. The other possibility is if it goes down. Right? And so that means one long one here. Okay, this is another possibility. Okay, now that's it for the left, because when it's left, it could be opposite. Actually, I didn't do that, did I? Yeah, left it could be opposite, left it could go up, or left it could go down. And so that's all of it. Now when it's right, it could go up, or it could go down, or opposite. Well, right opposite would be the same as this without moving any atoms. So the only other option is right down, like this. So how many resonance forms are there here? 1, 2, 3, 4, 5, 6 resonance forms for this. Right. And so what does a hybrid look like in this case? The hybrid is going to look like this. All the bonds are going to be equal. And so I get 4 equivalent bonds. But now I have 2 double bonds that are spread out or delocalized over the entire structure. When I have 2 double bonds, it's going to be like this, more electron density. And so the easiest way to figure out the bond order for this is to count out the total bonds. 2 for the double, 4 for 2 doubles, 5, 6. So I got 6 over 4 positions, so that's 6/4. 6/4 is what? 6/4. 6/4 is 1 2/4, or 1 1/2, right? And so what that means is that each of these bonds are 1.5 bonds, and they're the same. Okay, what about the charge on the oxygens? The charge on the oxygens, I have a total of -2 spread out over 4. -2 spread out over 4 is -2/4. -2/4 is -1/2. And so the formal charge on each oxygen is -1/2. Now, we got to make sure it all adds up, because all the formal charges have to add up to the net charge. And so do they? Well, I got -1/2 times 4 is -1. No, -2. Actually, they don't add up. I must have screwed up. Oh, you know why? Because the chlorine is plus. And so this -2 plus 1 gives us -1 net. And so it's right. Okay, so the hybrid is going to look like this. It's going to be tetrahedral with 109 bond angles. But you know what? This is series 3. I want to get rid of that formal charge completely on chlorine. And I can do that. I can get rid of the formal charge completely by making a structure like this. And so now when I look at this, I have a negative charge here and 0 for everything else. So this is going to be -1. So how many resonance forms will I have for series 4? Well, if I leave the top, then I can have right, left. And so let's go left, right, like this. In other words, we'll just move the single bond. That's probably easier. And so if I have the single bond on the bottom, that's one resonance form. Single bond on the left, that's another. Single bond on the top, that's another. And then finally a single bond on the left. And so I get 4 resonance forms for this, just moving the single bond. I wouldn't move the atoms. We don't move the atoms. So which structure is the best? Is it 1, 2, 3, or 4 for perchlorate? Well, there's problems with forming the double bonds. Let me tell you about some of the problems. The problems with forming the double bonds we're going to be looking at the next section. But since we're doing Lewis structures in this section, I need to talk about this, and we're going to look at more bonding theory in the next chapter. And but for right now, what you would say is probably the best structure is going to be a hybrid of the hybrids. A hybrid of the hybrids means you take all these, and these and then mix them into one hybrid structure. Does that make sense? And so it's between the two extremes, probably. Between the extreme where we have the +3 on chlorine to 0, somewhere in between. But anyway, so this is what a lot of people do. A lot of people just write down the two extremes and say, well, it's somewhere between, probably. The extreme of maintaining the octet but having high formal charge versus minimizing formal charge and expanding the octet. Okay. And so a lot of people, what they'll do is they'll just write down all the structures. Perchlorate's a tough one. Like chlorate's easier. I've given chlorate on tests in the past. But still, it's a lot of structures to draw out. Okay. All right, well, I'm going to stop talking here. Why don't you do your Lewis structures? And we'll check those, and then do the geometries for those. We don't have much time left. If you guys have questions on the test, let me know about the test. Because tomorrow we're off, right? And so we use the last part of lab today to go over any questions you have.